Okay, this is Physics 14.3, the last of the three sections for Chapter 14, and we want to look at wave behavior. Basically, we're going to look at what happens when waves hit a new medium, and we're also going to talk about the fact that waves can interfere with each other, and that interference could either be constructive or destructive. We'll get into more on that later, but we're going to want to introduce the concept. We're going to need that when we talk about light and sound. So, essential questions: how are waves reflected and refracted at boundaries? So we got some vocabulary there. And what do we mean by this idea of superimposition? So we're going to look at new vocabulary. We're going to talk about incident waves, reflected waves, principle of superimposition, interference, nodes, antinodes, standing waves, wavefront, rays, normal, a law of reflection and refraction. When you're all done, you should be able to explain what each of these terms mean. So a lot to do, so let's get started. When a wave encounters a boundary of a medium which it's traveling in, one or two things could happen. One, it could be reflected back, or some of it can go on through. And so those are the two things that will happen. We're going to look at both of these individually. Many times the properties of the wave results from the fact that the two or more mediums will exist at the same time. And again, think of those waves as energy passing through the thing, so it moves the particles up and down, but it doesn't move the particles down the string. But the wave motion can affect each other. So again, this is superimposition we're going to be talking about. So let's take a look at a simple example. We have two springs that are attached together, different types of springs, so they have different characteristics. We're going to call this a boundary between these two springs. And so the waves strike the boundary. The incoming wave we're going to call the incident wave. So that's your first vocabulary word. Whenever you hear incident angle or incident wave, we're talking about the original wave coming on in. The boundary is the point on which we have two waves that are two different mediums that are connected. So what happens? Well, if you have one big pulse coming in from the larger spring, it continues on into the smaller spring. We say it's transmitted. If the incident wave is up, the transmitted wave is going to be up. But you'll also notice that some of the energy that hit the incident, or from the incident wave, was reflected back. And so we can say that this is a reflected wave. Whether or not the reflected wave is upright or inverse is going to have, it depends on the characteristics of the boundary. We're going to see what happens when we have an inverse. Inverse would simply mean that the wave is going down. So if we attach the spring to a wall, then we're going to see, and we send a pulse down the spring, then what happens is when it hits that boundary, it tries to transmit energy into the medium, but it can't, so it comes back. Well, all the energy is reflected back, but you'll notice it's reflected back in an inverse wave. In other words, if you have a wave going up on the way out, it's inverse, or down on the way back. So again, almost all the energy is reflected back, and it's inverted. When the two different waves, or thinking of energy, are acting on the same thing, each wave affects the medium independently. I'm going to show you a little video to clear this up. The principle of superimposition states that the displacement of the medium caused by two or more waves is algebraic sum. We'll talk about that in a minute as well. Let's just watch this little video. Here we go. Okay, so once again, this idea of superimposition, basically super, meaning they're both at the same position, okay, states that the displacement is the algebraic sum. So if you have two waves that are coming in, if they're equal and opposite, then it goes to 0. But if they're not equal and opposite, then you could just add those numbers together. If one is pushing up with 1 meter by 1 meter, the other one's pushing up by 2 meters, add them together, you get 3 meters. Again, they could either cancel each other out, or they could kind of help each other to push the medium up. Now, what happens when you tie a rope to a door spring or a doorknob, and you lift up the rope to send a pulse down there? Well, the pulse gets to the other end. When it gets to the other end, so think of this blue line, you've sent this pulse down there. When it gets to the other end, that pulse is reflected back, and it's an inverse pulse. Well, let's say that instead of, so you have the pulse going out, you have the reflected pulse coming back. And it's inverted. Well, if you then send another pulse, a second pulse, down the string, and this time instead of going up, you're going down, you're sending a pulse down at the same time as your first pulse is coming back, and again inverted, trying to push it down. They're actually going to increase the amplitude of the downward push down to here. Now remember, you just sent this pulse down to this direction. It's going to be reflected back. So if at the same time you lift the rope up to send a pulse in the opposite direction, again, the pulse coming from the doorknob and your pulse are both going to work to move the rope up, and you'll have this pulse, or you'll have this swinging up and down, which is actually higher than the energy you're putting in, because you're getting the benefit of both your original pulse down and your return pulse, the energy from the return pulse coming back. And so you're going to have that constructive interference working on the rope to raise the rope. So you get, if you get the sequencing right, so that every time you lift the rope up and you send a pulse down from your end, you're mirroring the pulse returning from the previous pulse going the other direction, you're going to get this displacement, and the reflected will raise. So you're going to get an oscillation of the rope, and you're going to get a large amplitude oscillation. Again, this is this idea of resonance. If you remember the bridge collapse in the first video, that was a result of this oscillation, increasing until finally the bridge collapsed. Now what's going on in the other two pictures here? Well, we're going to find when we study sound in particular that we could that if we know what the frequency is to cause this to happen, if we double that frequency, we could actually get more standing waves to set up. This, by the way, is called a standing wave when you have a shape that the string apparently looks like it's like this. It's called a standing wave. You could actually double that. And again, if this is a node and this is a node and this is the antinode, if you double the frequency, this middle part now becomes a node because it's not moving, and you have two antinodes. Alright, so the standing wave is the interference of two opposite waves. If you double the frequency, you can produce more than one node. If you change the frequency again, you can get more nodes to show up. Now this doesn't happen all the time. If you change the if you don't change the frequency correctly, all you'll end up doing is having it cancel each other out. So, and I'm going to show you an example of that. I got a really cool setup that we can look at that. So again, furthering changing the frequency, we can get it to change up more. Okay, so what happens when you throw a rock in a pool? So now we want to look at a series of waves. When the rock goes in, you can see we have a series of waves generating out. You could sketch those as circles, and again, another way of doing this is if you put your fingers in some water and you result a constant frequency, then you're going to have a whole bunch of concentric circles. Instead of just a couple of them, you're going to get a whole bunch of them. The wave front, we're going to talk about what the wave front is. Basically, it's where the crest of the wave is, and it could be shown in the following shape. So here's, if you have something that you're agitating the water right there and it's setting out ripples, the wave front is the front right out here. So we have 1, 2, 3, 4 wave fronts depicted here. If you measure the distance between one wave front to the next wave front, you're going to get the wave length. You can't see the amplitude. To see the amplitude, we have to turn this on its side and look at it in cross section to see how big these waves are. That would be the amplitude. But we can measure the wave length just simply by looking at the distance from one crest to the next. The other thing we have depicted in here are these rays. And the idea of a ray is, if you look at the energy it's going out, now there'd actually be almost an infinite number of rays in all directions. But to make life simpler, oftentimes we'll just pick one ray to focus on. And again, if we draw a line that's at right angles to the wave fronts, we can basically, we'll have a ray and we'll say, okay, we have energy going out in this direction. Again, something like this, we have energy going out in all directions. But we could also do something where we basically focus all the energy in one ray to be able to make life a little bit simpler. And so here we have a laser beam being shot into some water. And we see a number of interesting things. We have the medium right here. Okay, this is the boundary layer between the two mediums. This is probably air, most likely water, but anyways, it doesn't really matter exactly what they are. We also have a line that's normal to the medium, okay? And it doesn't really matter where I put this, but we'll put it here. We have the incident ray coming in. You'll notice that there's a reflected ray coming out. It's just reflecting off the surface of the water. There's probably a meniscus going on in here, this thickness. I got a diagram that actually clears a little bit of this up. We also have this idea of a transmitted ray continuing on through into the medium, but it's changing direction. If you look at the angle right here, from the normal to the angle, that's going to be the angle of incidence. If you look at the angle right here, this is the angle of reflection, because that's the reflected ray. And again, if you look at this angle right here, this is the angle of incidence, and if you look at this angle down here, this is the angle of transmission or refraction. So let's take let's look at a diagram that's a little easier to see. Here we have again our normal, and here this is labeled as the, if we have a nice clean boundary where basically it's just like there's no meniscus or anything, it's just right there. Okay, we have the angle, this is the incident ray, this is the reflected ray, this is the transmitted ray. The incident ray has an angle of incidence from the normal. Don't measure this angle down here. It's this angle up here. The reflected ray coming back off, same angle. These two angles are equal to each other. The reflection is always at the same angle from normal as the incident ray. However, the transmitted ray is changed because we have two different mediums. We have a different angle of refraction. This is this idea of refraction. Sometimes if you've ever looked at a spoon in a glass of water and it looks like it's disjointed, you're seeing this idea of refraction. Okay. So anyways, that's refraction. So the direction of the normal again is shown as this line. It's perpendicular to the barrier. This is the blue line was a barrier. The angle of the incident ray and the from the normal is called the angle of incidence. The angle between the normal and the reflected is called the angle of reflection, and the law of reflection states that the angle of incidence is equal to the angle of reflection. We also have refraction. The change in the direction of an angle as it leaves the boundary is called the angle of is known as refraction. The angle of refraction down here is also measured from normal. Okay, so it's going to be on the other side, but it's also measured from normal. And most of the time it's going to be different. If the mediums are different, they probably have a different index of refraction, so they're going to have a different angle of refraction, and you can see refraction occurring. Now the other thing that happens with the refracted ray is that the wavelength is going to change. Okay, the transmitted ray, the wavelength is going to change. The frequency doesn't change. If you think of this as consisting of a bunch of waves coming in, the number of waves that hit the boundary have to equal the number of waves leaving the boundary. So the waves per second that enter the boundary and leave the boundary are the same. The frequency at the boundary does not change. So what has to give? Something has to give someplace. It just makes sense. Well, remember that the medium determines the wave speed. Okay? So if this is one medium up here like air, and this is a different medium like water, the wave is going to travel at a different speed in the water than it does in the air. It's going to travel the fastest in the air of anything. Actually, in a vacuum, it travels the fastest. If it's light. If it's sound, again, air generally. But anyways, so it's based on this idea of the wavelength, lambda, is equal to the velocity divided by the frequency. Well, if the frequency is not changing, but the velocity is, if the velocity goes down, then obviously the wavelength has to go down. If the velocity increases, then the wavelength has to increase. So we're going to be doing some math, not this chapter, but next chapter. But I wanted to introduce all these concepts so we're ready. You may also be aware, not be aware, that the echoes are caused by reflection of the sound off of hard surfaces. So next time you're with your little niece or nephew and you're yelling across the canyon, say, what you're experiencing is reflection of sound waves. Refraction. Again, if you want to take all the fun out of rainbows, point out that the reason why the light you see the rainbow is because the raindrops are refracting the light and basically separating it out into different colors. And that's it.